All right, hi everybody. In this video, we'll walk through problem 9b in activity 5.7 about tipping forces. We have a sign here. Hopefully you can see the dimensions on the camera. It's 18 by 18 base, 60 inches, which measures from the base to the bottom of the sign portion at the top, and another 24 to the very, very top of the sign. That's a 24 by 24 square. We're given some information here. The information we're given is that the sign weighs 40 pounds, and that the force from the wind that's trying to tip it over is 13.2 pounds of force. And again, that's from the wind. And they also tell us it's applied at the geometric center of the top. So they're saying it's applied right here at the center of this square piece at the top. The question is that enough force to tip it over? Okay, so what we need to do then, I'm going to draw another view of this just to give us a little bit more perspective. Okay, this is going to be a side view, and it's going to be kind of, you know, a really quick little thing here. But it might look like this, okay? So let's say that this is like the sign again, okay? And we're looking at it from the side now, as opposed to from like an isometric view, okay? And what we know is if the wind is applied right here, okay? And again, that's a 13.2 pound force. So let's say it's pushing on the front, that this thing would tip over, and the point that it would rotate around, the fulcrum in this case, would be about right there, right? So we'll call that like P, just like we did with the first problem. The other things that we know is that thing looks very geometric to me. So which means that center of gravity, if we're looking at this view, the center of gravity is going to be somewhere in the middle. It's going to be somewhere right about there. But if we're looking at it from the side, again, it's symmetrical. So it's going to be dead centered for this thing too. So I'm going to use a different colored marker here. And let's say that the center of gravity is about right there, right? Now, I don't know how high up it is. I don't have a clue. But what I do know is that it's pointing downward, okay? So if I were to draw an arrow representing the weight of the object, I would know that it'd be 40 pounds and it would be downward, okay? So that's what I know so far. So what I have then is, if we have rotational forces, just like we did in the first problem, we have rotational forces, moments. I know that counterclockwise and clockwise are going to equal each other. So I can go like this, and I can say, you know what, if that was going to rotate, there's my rotation point, right? Okay, that would be a counterclockwise rotation, okay? And I know that this 40-pound force would be applied at a 90-degree distance. If I was interested in this, this is the distance I would need, okay? The 90-degree distance, which is from right here to here. Well, if that's 18 by 18, that means that this would be 9 inches, right? Wherever I draw, whether I'm drawing at the top or the bottom, it truly does not matter. It's the same exact thing, okay? So I have a 40-pound force applied at a perpendicular distance of 9 inches, okay? So when I set later on counterclockwise equal to clockwise, I know that I'm going to have a 40-pound force applied at a distance of 9 inches. Okay, so that's part one. Now, something is counteracting that, and the thing that is counteracting that, I'm going to use different colors. I'm going to run out of space here. So I'm going to get rid of this for a second just to kind of clear the picture up. I know that this 13.2 pound force, if it was going to rotate it, it would rotate it this way, because there's my fulcrum, right? So imagine this teeter-totter, you're pushing this way. Okay, there's the rotation. So this is going to go the opposite direction. That's clockwise, not counterclockwise. This is the counterclockwise force. There we go, okay? And here's what I know. Good. Keeps my color coding here. I know that a 13.2 pound force is applied, but I need to know the 90-degree distance, the perpendicular distance. So what I'm really curious about is, what is the distance from the very bottom, this center of rotation right here? How far is it to the geometric center of the sign at the top, right? This is the distance that I need. So what I have is this 60 inches plus halfway up the sign, which would be another 12, right? And 60 plus 12 is 72 inches total. So I have a 13.2 pound force applied at a distance of 72 inches. Now, the question is, look, no variable, right? No variable. And that seems a little bit weird, but what I want to know is, if this number that I get out of this is greater than this number, then I know that this moment must be bigger than this moment, which means that the rotational force this way will overpower the rotational force from the weight of the object that wants to keep it still. So let's multiply it out. What is 40 times 9? That's fairly simple. That's 360. Notice, by the way, pounds, inches, right? So I know that I'm being consistent there, okay? And then on the other side, if this number is greater than 360, then I know that I have enough force to take care of that, right? So let's see here, 13.2 times 72 is 950.4. That would be pound inches. That would be the unit that I'd be using. Seems weird, but it's a torque. That's what I'm interested in, or a moment, okay? This one is way bigger than the 360 that I'm given to keep it in place, okay? So what I know is, yes, it will tip over. That's the first portion of the problem. I'm gonna cut the video off there, because the next question is, how many sandbags can I add to the bottom to keep this thing in place, okay? And we'll go over that in the next video. Hopefully that makes sense. If you got any questions, feel free to ask me in class.